Hello there, and welcome back to Sleeping with Science Stories. Tonight, let me guide you into a gentle journey through the most wondrous things in the universe. A journey without hurry or noise, soft as the starlight at night, like a cool breeze drifting through the leaves. If this is your first time visiting the channel, or if you are looking for better sleep with science, please hit subscribe and turn on notifications. Every night, we have a new story to relax together, to explore together, and to drift into a peaceful sleep together. Did you know that right at this very moment, as you are lying here, the Earth is rushing through space at nearly 830,000 kilometers per hour, along with the Sun and billions of other stars in a gigantic orbit that is slow but never stopping around the center of the Milky Way. And the Milky Way, our galaxy, is not just a shimmering band across the night sky. It is a world so vast it is almost unbelievable, with 200 to 400 billion stars, trillions of planets, enormous clouds of gas, and mysteries still without answers. Tonight, we will not rush. Let the numbers, the images, and the scientific facts slowly sink into your mind like stars gradually appearing in the night sky, naturally, softly, and enchantingly. Now close your eyes if you want, or let them rest loosely on a distant point, and begin this journey with me. The journey through 1001 facts about the Milky Way. Imagine 13 billion years ago, when the universe was still young, only a few 100 million years old after the Big Bang. At that time, space was hazy with a thin mist of primordial hydrogen gas, no stars yet shining, and no galaxies formed. But within that eternal silence, gravity was whispering. It was pulling clouds of gas closer together, slowly and patiently. From those clouds, the first seeds of the Milky Way began to take root. The Milky Way did not emerge as a complete galaxy from the start. It was not like a building constructed from a perfect blueprint. Instead, it was like a river formed from hundreds or thousands of small streams, each carrying its own story and origin, all merging into one magnificent flow. The Milky Way was born from mergers, from gentle and sometimes violent collisions with dozens or hundreds of smaller galaxies throughout its ancient history. Over the past 13 billion years, the Milky Way has swallowed and merged with many smaller galaxies. Scientists call this process hierarchical merging, a scientific term that may sound dry, but behind it lies a dramatic story about survival, dominance, and constant transformation. Each collision between galaxies is nothing like two cars crashing on a highway. There are no explosions, flames, or instant destruction. Instead, it is like two clouds of smoke drifting into each other in a light breeze. Stars in colliding galaxies do not crash into each other because the distances between them are far greater than their own sizes. If the Sun were a tennis ball, the nearest star would be more than 1,000 kilometers away. In a galactic collision, stars simply pass by one another like lone boats on a vast ocean. Gravity behaves differently. It needs no physical contact. It pulls, twists, and bends space and time. As two galaxies approach, their gravity interacts. Spiral arms stretch and distort, forming long bridges of stars thousands of light years across. Gas and dust clouds collide, creating shock waves that compress them and trigger the birth of new stars. It is a slow yet powerful dance unfolding over hundreds of millions of years. Eventually, the two galaxies become one. Astronomers have discovered evidence of these ancient collisions in the structure of the Milky Way. They have found long stellar streams, thin strands of stars stretched across the galactic halo, remnants of small galaxies torn apart by the Milky Way's tidal forces. One of the most significant discoveries is the Sagittarius stream, a dwarf galaxy being slowly shredded and consumed by the Milky Way. It stretches into a giant arc wrapping around our galaxy like a delicate ribbon dissolving in the wind. This is not only the past. Even now, as you lie here listening, the Milky Way is consuming nearby dwarf galaxies. The Large Magellanic Cloud and the Small Magellanic Cloud, the two largest satellite galaxies of the Milky Way, about 160,000 and 200,000 light-years away, are being drawn closer. The gravity of the Milky Way is pulling gas and stars from them, forming a massive stream called the Magellanic Stream, which stretches across half the sky. In billions of years, these small galaxies will dissolve completely into the Milky Way, and their stars will become part of us. The story of collisions is not over. It has not even reached its climax. In about 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy, our largest neighboring galaxy, located 2.5 million light-years away. Andromeda is a giant spiral galaxy, slightly larger than the Milky Way, with around 1 trillion stars compared to our 200 to 400 billion. It has also consumed smaller galaxies in the past, and now it is moving toward us at about 110 kilometers per second. Nothing can stop this collision. The two galaxies are gravitationally bound, and the distance between them shrinks every second. Imagine that scene. In about 2 billion years from the surface of Earth, if anyone is still around to observe, they will see Andromeda grow larger in the night sky. At first, it will appear as a faint blur of light, but gradually it will swell and occupy more space. After 3 billion years, it will appear twice the size of the moon in our sky. Then the collision will begin. Do not picture it as a violent explosion. Stars will not collide directly. Instead, the two galaxies will begin a complex dance, a cosmic waltz lasting billions of years. They will sweep past each other, their spiral arms stretched and distorted by tidal forces. Gravity will pull them back, and they will collide again more forcefully. Gas and dust clouds will crash, triggering starburst events where millions of new stars are born. The night sky will blaze with the light of countless supernovae, massive stars living fast and dying young in spectacular explosions. After billions of years of dancing and colliding, the two galaxies will eventually merge into one. Their spiral arms will dissolve, torn apart, and blended together. The new structure will no longer be a spiral galaxy, but likely an elliptical one, a giant sphere of trillions of stars orbiting a common center. Scientists have named this future galaxy Milky Way, or Milkdromeda, a poetic fusion of Milky Way and Andromeda. It is a beautiful name for a grand event that will reshape our entire local galactic group. But do not worry about the fate of the Earth or the Sun. Computer simulations show that there is very little chance the solar system will be directly affected by this collision. The stars are too far apart, and the probability of a direct impact is extremely low. Instead, the solar system will most likely be pushed into a new orbit within the new galaxy, possibly farther from or closer to the galactic center, but still intact. We will simply be a tiny speck of dust drifting in a colossal wind, but a speck that survives. Of course, by that time, there will likely be no one left on Earth to witness it. The sun will have aged significantly, and in about 5 billion years it will begin to turn into a red giant star, engulfing the inner planets such as Mercury, Venus, and possibly even the Earth. Some stars in the Milky Way are actually older than the galaxy itself. How is that possible? How can a star be older than its own home? The answer lies in the collisions we just discussed. When the Milky Way merged with smaller galaxies in the past, it did not only pull in gas and dust to form new stars, it also absorbed the stars that already existed in those galaxies, stars that formed 12 or even 13 billion years ago, from a time when the universe was still very young and only a few 100 million years old. These stars are called metal-poor stars, and that term needs some explanation. In astronomy, the word metal does not refer only to elements like iron, copper, or gold, but to all elements heavier than hydrogen and helium. In the early universe, after the Big Bang, only 3 elements were created: hydrogen, helium, and a small amount of lithium. All other elements, from carbon, oxygen, and nitrogen to iron, gold, and uranium, were created later inside the cores of stars and in supernova explosions. Therefore, a metal-poor star is a star born from nearly primordial gases that has not been enriched by previous generations of stars. Astronomers hunt for these stars the way archaeologists search for ancient artifacts, because they are precious windows into the distant past of the universe. By analyzing the light from these stars, by splitting the light into its different colors and studying the spectral lines, scientists can determine their exact chemical composition. In some rare cases, they find stars with metallicity only 1/1,000,000th that of the Sun, meaning they are composed almost entirely of primordial hydrogen and helium. One of the oldest stars ever discovered is named HE 1523-0901, a red giant star located about 7,000 light-years away. By measuring the amount of radioactive elements in this star and calculating their decay rates, scientists estimate its age to be around 13.2 billion years, only 500 million years younger than the universe itself. It is a star that has witnessed nearly the entire history of the universe, a star born in its childhood and still shining today. But how can these stars be older than the Milky Way? The answer is that they are not truly older than the galaxy in an absolute sense. They were born in other primordial galaxies, galaxies that formed before the Milky Way and were later absorbed by it. These stars are therefore migrants, refugees from lost worlds, now living in a new galaxy where they were not originally native. This tells us that the Milky Way is not a single uniform entity, but a complex collection of many generations of stars with many different origins, all blended together over billions of years. It is like a large city where centuries-old houses stand beside modern buildings made of glass and steel, where native residents live alongside immigrants from all over the world. Together, they form a rich, diverse, and constantly evolving tapestry. The Milky Way is not a finished galaxy that has reached its final stable state. It is still growing and still gathering material from its surroundings. It is expanding like a living organism. This process unfolds slowly on astronomical timescales, but it is happening right now as you listen to these words. Each year, the Milky Way absorbs about 1 to 2 solar masses of intergalactic gas. This gas consists of cold hydrogen streams drifting in the space between galaxies, leftovers from the Big Bang and from supernova explosions in other galaxies. This gas does not arrive randomly. It is pulled in by the immense gravitational field of the Milky Way. As it falls into the galaxy, it is heated by friction, compressed by pressure, and eventually condenses into molecular clouds where new stars are born. This process is crucial for the life of the galaxy. Stars do not live forever. They are born, they live for millions or billions of years, and then they die, often in supernova explosions or by gently shedding their outer layers into space. When stars die, they return some material to the galaxy, but a significant portion becomes locked inside dead remnants, such as white dwarfs, neutron stars, or black holes. Without new gas from outside, the galaxy would slowly run out of material to form new stars, and star formation would gradually slow down and eventually stop. But the Milky Way does not only absorb gas. It also consumes dwarf galaxies, tiny satellite galaxies orbiting it like moons around a planet. We have mentioned the large and small Magellanic Clouds, but there are dozens of other dwarf galaxies, faint and difficult to observe, with only a few million or a few tens of millions of stars. These small galaxies cannot resist the gravitational pull of the Milky Way. Gravity draws them closer and closer, and eventually, when they come too close, tidal forces begin to tear them apart. Their stars are pulled away, forming long stellar streams that wrap around the Milky Way like delicate threads. A well-known example is the Sagittarius dwarf galaxy, a small elliptical galaxy that is being slowly ripped apart by the Milky Way. Astronomers have discovered that it is being stretched into a massive arc surrounding the Milky Way, and its stars are gradually dissolving into our galaxy. In billions of years, Sagittarius will disappear completely, and its stars will become indistinguishable from other stars in the Milky Way. And then there is dark matter, the mysterious substance that we cannot see or touch, but which makes up about 85% of the galaxy's mass. Dark matter does not emit light, does not absorb light, and does not interact with normal matter except through gravity. We know it exists only because we can observe its gravitational effects on stars and gas in the galaxy. Like gas and dwarf galaxies, dark matter is also being pulled in by the Milky Way, gathering into an invisible dome, a massive halo surrounding the entire galaxy and preventing it from flying apart under the centrifugal force of its rotation. Thus, the Milky Way is like a living organism that is breathing, feeding, and growing. It is not a static structure, but a dynamic entity that is constantly changing and evolving. And we, small beings living on a small planet orbiting an average star, are part of this grand process, whether we are aware of it or not. We know the Milky Way is a spiral galaxy with curved arms extending outward from the center like swirling waves on water. But how many arms are there exactly? 2, 4, or more? The answer is that we are not certain, and the reason is simple. We live inside the galaxy. Imagine standing in the middle of a dense forest with towering ancient trees blocking the sky and thick underbrush hiding your view. Now try to draw an accurate map of the entire forest, identifying its boundaries, its pathways, and its dense and sparse regions. It is an extremely difficult task, if not impossible, when you can only see a few dozen meters around you. The only way to create a good map is to rise above the forest, look from above, and observe the entire landscape from a panoramic view. That is exactly the problem astronomers face when trying to map the Milky Way. We live inside the galaxy, about 27,000 light years from the center, and we cannot fly outside to look back. Moreover, the galaxy is full of cosmic dust, tiny particles of carbon and silicate floating in space, which obscure the light from distant stars. In visible light, we can see only a few thousand light years through the galactic disk before everything is dimmed by dust. This means we cannot view most of our galaxy in ordinary light. However, astronomers have found other ways to study the structure of the Milky Way. One of the most effective methods is to use radio waves. Cosmic dust does not block radio waves, so we can observe through the entire galactic disk with radio telescopes. In particular, scientists observe the 21-centimeter spectral line of neutral hydrogen, a characteristic line emitted by hydrogen atoms when their electron changes its spin state. By measuring the intensity and frequency of this line from many directions, they can map the distribution of hydrogen gas in the galaxy. They also use infrared light, which is less affected by dust than visible light. By observing young, bright, hot stars that typically concentrate in spiral arms, they can sketch the shape of those arms. And recently, with the help of the Gaia satellite, a spacecraft of the European Space Agency launched in 2013, scientists have measured the positions and velocities of more than 1 billion stars in the Milky Way. This data allows them to create an unprecedented three-dimensional map of our galaxy. Even with all these advanced tools, the question of how many spiral arms there are remains unresolved. The currently most common hypothesis is that the Milky Way has 4 major arms: Perseus, Norma, Scutum Centaurus, and Sagittarius. But some studies argue there are only 2 main arms and that the others are smaller spur arms. Other studies suggest there may be more than 4 arms, or that the true structure is far more complex than a simple spiral model. The problem is that spiral arms are not clear, sharp structures like real limbs. They are regions of slightly higher stellar density, areas where stars and gas concentrate more. The boundary between an arm and the interarm region is not sharp, but fades gradually. Moreover, stars are not fixed to their arms. They move into and out of the arms as they orbit the galaxy, like cars moving through congested lanes on a highway. It is a strange and humble thing that we can observe galaxies millions or even billions of light years away in astonishing detail, count their spiral arms, and measure their mass and rotation, yet we cannot clearly see our own home. It is a reminder that sometimes the things nearest to us are the hardest to understand. In illustrations and textbooks, the Milky Way is often drawn as a perfectly flat, symmetric disk with spiral arms harmoniously winding from the center outward. That is a beautiful, ideal, and easy to understand image. But in reality, as usual, it is far more complex and messy than theory. The galactic disk is not flat. It is warped and distorted, like a plastic plate left in the sun too long, or like a twisted pizza. The edges of the disk, especially beyond about 30,000 or 40,000 light years from the center, are not on the same plane but bend up and down, forming a shape called a warp. On one side, the disk bends up from the central plane by about 3,000 light years, and on the other side, it bends down by the same amount. Why does this happen? There are many reasons, and it is the result of complex interactions among several forces. One major cause is the gravitational pull from surrounding dwarf galaxies, particularly the Large Magellanic Cloud and the Small Magellanic Cloud. Although much smaller than the Milky Way, these two satellite galaxies still have enough mass to exert a significant gravitational influence. As they orbit the Milky Way, their tidal forces pull on the edges of the galactic disk, deforming them. This is the same phenomenon that creates tides on Earth due to the gravitational pull of the Moon and the Sun. But on a galactic scale, it is far larger. A second reason is dark matter. We mentioned that dark matter forms a huge halo around the Milky Way, but this halo is not perfectly symmetric. It can be distorted, with regions denser or more rarefied, and this uneven distribution creates zones of stronger and weaker gravity. Variations in the gravitational field can pull different parts of the disk in different directions, producing the warp. A third reason is the non-uniform rotation of the galaxy. Different parts of the Milky Way rotate at different rates. Near the center, things rotate faster, and farther out, the rotation speed decreases, but not in a simple way. In fact, one of the great mysteries of astronomy is the flat rotation curve of galaxies. According to Keplerian motion, rotational speed should decline with distance from the center, like planets farther from the Sun, moving more slowly. Observations, however, show that the rotation speed of stars at the galaxy's edge remains nearly constant, and this is one of the strongest pieces of evidence for the existence of dark matter. This non-uniform rotation generates shear, a stretching force in the galactic disk. Some parts of the disk are pulled ahead faster, while other parts lag behind, producing spiral waves, ripples that propagate through the disk and cause it to warp and distort. Scientists have used computer simulations to study this process and have found that the disk's warp can change over time, not a fixed structure, but a dynamic feature that evolves on timescales of hundreds of millions of years. There are other asymmetries in the Milky Way's structure as well. For example, the central bar, a bar-shaped structure extending through the galaxy's core, is not perfectly straight, but slightly bent. The spiral arms are not completely regular. They have dense and sparse regions, bright and dim patches. The distribution of gas and dust is also uneven, concentrated in some areas and sparse in others. All of this tells us that the Milky Way is not a perfect structure drawn from an ideal blueprint. Instead, it is a living entity constantly changing and subject to countless invisible forces. It is the product of 13 billion years of evolution, of innumerable collisions, mergers, and interactions. It is precisely this imperfection, this distortion, this asymmetry that makes it more beautiful, more real, and more wondrous. Imagine flying very high, above the atmosphere, beyond the moon, past the planets of the solar system, and continuing outward until the entire solar system is only a small, bright dot in the darkness. Then keep flying past thousands and millions of stars until you can finally see the whole Milky Way from the outside as a gigantic glowing disk in the cosmic night. From that viewpoint, you would see a beautiful and complex structure, an architecture built not by any architect, but by the laws of physics, by gravity, by motion, and by time. Right now, as you lie still and feel complete silence, your body is moving through space at an almost unimaginable speed. The Earth rotates on its axis at about 1,600 kilometers per hour at the equator. At the same time, it orbits the Sun at about 107,000 kilometers per hour. But that is only the beginning. The Sun, along with the entire solar system, moves around the center of the Milky Way at roughly 828,000 kilometers per hour, or about 230 kilometers per second. That is a staggering number. To gain some sense of it, think that this speed is about 600 times the speed of a rifle bullet and about 20 times the speed at which the Earth orbits the Sun. This journey is not quick. It takes about 225 to 250 million years for the solar system to complete one full orbit around the galactic center. Astronomers call this time span a galactic year. To put this number in context, the last time the solar system was in its current position in the galaxy was about 200 million years ago, during the Triassic period, when dinosaurs were first appearing on Earth. Since Earth formed about 4.5 billion years ago, the solar system has completed roughly 20 orbits around the galaxy. The orbit is not a perfect circle. It is slightly elliptical, meaning sometimes we are closer to the galactic center and sometimes we are farther away. At present, we are at an average distance of about 27,000 light-years from the center. In the past, we have been closer, perhaps only 25,000 light-years away, and we have been farther out, possibly as far as 30,000 light-years. Furthermore, the solar system does not move only in the plane of the galactic disk. It also oscillates up and down through this plane, like a boat bobbing on ocean waves. This oscillation cycle takes about 60 to 70 million years. Sometimes we are above the galactic plane, sometimes below it, and sometimes we pass through it. Currently, we are a few dozen light years above the galactic plane and are moving toward it, crossing it in a few million years. This oscillation may affect life on Earth. When we pass through the galactic plane, where the density of stars and gas is higher, we are more likely to encounter phenomena such as nearby supernovae, stronger cosmic rays, or even cold gas clouds that could disturb the Oort cloud, the reservoir of trillions of comets at the edge of the solar system. Some scientists have proposed that this oscillation may be related to cycles of mass extinctions on Earth, although this hypothesis remains controversial and unproven. But the solar system is not the only thing in motion. The entire Milky Way is moving as well. It is heading toward the Andromeda Galaxy, as we discussed, but it is also moving with the Local Group, a collection of about 50 galaxies that includes the Milky Way, Andromeda, and many dwarf galaxies. The Local Group itself is being pulled toward a larger structure called the Virgo supercluster, a massive assembly of thousands of galaxies spanning roughly 100 million light-years. The Virgo supercluster is not stationary either. It is moving toward an even larger structure called Laniakea, one of the largest structures in the observable universe, containing on the order of 100,000 galaxies. Thus, we are moving on many nested levels. Around the Sun, with the Sun around the galaxy, with the galaxy toward Andromeda, with the Local Group toward the Virgo supercluster, and with Virgo toward Laniakea. It is a complex cosmic dance, a system of motions within motions that we do not perceive in everyday life. When people talk about the solar system's location in the Milky Way, many assume we are located in one of the main spiral arms, the large arms that curve from the center outward. In reality, we are not. We reside in a smaller structure, a branch called the Orion Spur, also known as the Orion Arm. The Orion Spur is not one of the galaxy's major arms. It is a minor branch sitting between two large arms, Perseus and Sagittarius. Its length is only about 10,000 light-years compared with the tens of thousands of light-years of the major arms. It is a relatively quiet region, not as densely populated with stars as the main arms, and not home to many supernovae or extremely bright massive stars. But this may be good fortune for life. In the main spiral arms, where stellar density is high, many massive stars are born and die in powerful supernova explosions. These explosions emit enormous amounts of radiation, including X-rays and gamma rays, which can be harmful to any planet within a radius of a few dozen light-years. If a supernova exploded close enough to Earth, it could destroy the ozone layer, increase ultraviolet radiation at the surface, and cause a mass extinction. In the Orion Spur, that risk is much lower. A lower stellar density means fewer supernovae, and therefore a more stable environment for the development of life. Some scientists have proposed that our location in a relatively quiet region of the galaxy may be one of the factors that contributed to the emergence and evolution of life on Earth. This is part of what is called the galactic habitable zone, the habitable region of a galaxy, a concept similar to the habitable zone around a star, but applied to the entire galaxy. The galactic habitable zone is a ring-shaped belt around the galactic center that is not too close and not too far. Too close to the center, the stellar density is too high, with too much radiation, too many potential collisions, and a supermassive black hole at the center that can produce high-energy phenomena. Too far from the center, the metallicity, meaning the abundance of elements heavier than hydrogen and helium, is too low, leaving insufficient material to form rocky planets and the complex molecules necessary for life as we know it. The solar system lies within this zone at a moderate distance from the center, in a quiet spur, with enough metals to form rocky planets and life, but not so much violent cosmic activity. That may be a lucky coincidence, or it may be a necessary condition for life as we know it to arise. This question remains one of the major open questions in astrobiology. At the center of the Milky Way, in the region called the galactic center, there is a special object that for decades astronomers could only detect indirectly. That object is a supermassive black hole called Sagittarius A star, or abbreviated SGAR-A star. This black hole has a mass of about 4 million times the mass of the Sun, but its size, meaning the radius of the event horizon from which nothing can escape, is only about 24 million kilometers, smaller than Mercury's orbit around the Sun. That is an incredible density, an enormous amount of mass compressed into an extremely small space. For many years, astronomers suspected the existence of this black hole based on the motions of stars near the galactic center. They observed some stars moving at extremely high speeds, up to a few percent of the speed of light, on elliptical orbits around a central point that appeared to contain nothing visible. By tracking the motions of these stars over many years, even decades, they could calculate the mass of the invisible object at the center, and the results pointed to a supermassive black hole. One of the most studied stars is S2, sometimes called S02. This star orbits SGRA star on an orbit with a period of only 16 years. And at its closest approach, it reaches a speed of about 2.5% of the speed of light, which is roughly 7,500 kilometers per second. Observations of this star provided the strongest evidence for the supermassive black hole, and this work led to the 2020 Nobel Prize in Physics for astronomers Reinhard Genzel and Andrea Ghez. But the black hole cannot be seen directly in visible light because nothing can escape from it. So how can we see it? The answer is through radio emission. Matter falling toward a black hole does not fall straight in, but spirals around it in an accretion disk. And in the process, it is heated to extremely high temperatures and emits radiation at many wavelengths, including radio waves. In 2019, an international project called the Event Horizon Telescope, using a network of radio telescopes around the world to create an Earth-sized virtual telescope, released the first image of a black hole. Not of SGAR-A star, but of the black hole at the center of the galaxy M87, about 54 million light-years away. That image showed a ring of light surrounding a dark region, exactly as Einstein's general relativity predicted. In May 2022, the Event Horizon Telescope team also released the first image of SGAR-A star, the black hole at the center of our galaxy. Although the image is somewhat blurred and difficult to interpret due to the distance and the variability of the surrounding material. It remains an extraordinary scientific achievement, the first time we have seen the dark heart of our galaxy. A star is not a highly active black hole. It is relatively quiet compared with some supermassive black holes in other galaxies that are devouring large amounts of matter and emitting powerful radiation. But occasionally it does flare, times when infalling material emits X-rays or gamma rays. Scientists believe that in the past, SGR, a star, may have been much more active, and it could become active again in the future if more material falls in. Looking at images of other spiral galaxies, we see that many of them have a bar-shaped structure across their nucleus, and the spiral arms often begin at the ends of that bar. Such galaxies are called barred spiral galaxies, as opposed to ordinary spiral galaxies without a bar. The Milky Way is a barred spiral galaxy. The central bar of the Milky Way is about 27,000 light-years long, stretching from one side of the galaxy to the other and passing through the center where CGR-A star sits. It is not perfectly straight, but slightly curved and twisted, and it rotates at a pattern speed different from the rotation of the surrounding galactic disk. This bar plays an important role in the structure and evolution of the galaxy. It acts like a pump, moving gas and stars from the disk into the central regions, feeding the supermassive black hole and fueling star formation in the central area. At the same time, it generates complex orbital patterns and resonances that cause some stars and gas to concentrate into rings and spiral features. But the story is more complicated. Some recent studies suggest the Milky Way may have not just one bar, but two. There could be a smaller bar within the larger bar, a nested structure rotating at a different speed. The idea of a bar within a bar is still debated and requires more observations to confirm. But if true, it would make the Milky Way's structure far more complex than previously thought. The formation of bars in galaxies is a natural process that arises from gravitational instabilities. As a galactic disk rotates, any small perturbation in the mass distribution can be amplified by gravity, forming more organized structures. The bar is one such structure, a product of self-organization in a many-body system. Computer simulations show that many spiral galaxies, if not all, will develop bars at some point in their history, and these bars can persist for billions of years or dissolve and reform depending on conditions. The Milky Way's disk is not a homogeneous structure. It actually consists of two main components, the thin disk and the thick disk. These two components differ in thickness, in composition, in the ages of their stars, and in their motions, and this may be good fortune for life. In the main spiral arms, where stellar density is high, many massive stars are born and die in powerful supernova explosions. These explosions emit enormous amounts of radiation, including X-rays and gamma rays, which can be harmful to any planet within a radius of a few dozen light years. If a supernova exploded close enough to Earth, it could destroy the ozone layer, increase ultraviolet radiation at the surface, and cause mass extinctions. In the Orion Spur, that risk is much lower. A lower stellar density means fewer supernovae and therefore a more stable environment for the development of life. Some scientists have proposed that our location in a relatively quiet region of the galaxy may be one of the factors that contributed to the emergence and evolution of life on Earth. This is part of what is called the galactic habitable zone, the habitable region of a galaxy, a concept similar to the habitable zone around a star, but applied to the entire galaxy. The galactic habitable zone is a ring-shaped belt around the galactic center that is not too close and not too far. Too close to the center, the stellar density is too high, with too much radiation, too many potential collisions, and a supermassive black hole at the center that can produce high-energy phenomena. Too far from the center, the metallicity, meaning the abundance of elements heavier than hydrogen and helium, is too low, leaving insufficient material to form rocky planets and the complex molecules necessary for life as we know it. The solar system lies within this zone at a moderate distance from the center in a quiet spur, with enough metals to form rocky planets and life, but not so much violent cosmic activity. That may be a lucky coincidence, or it may be a necessary condition for life as we know it to arise. This question remains one of the major open questions in astrobiology. At the center of the Milky Way, in the region called the galactic center, there is a special object that for decades astronomers could only detect indirectly. That object is a supermassive black hole called Sagittarius A star, or abbreviated SARE star. This black hole has a mass of about 4 million times the mass of the Sun, but its size, meaning the radius of the event horizon from which nothing can escape, is only about 24 million kilometers, smaller than Mercury's orbit around the Sun. That is an incredible density, an enormous amount of mass compressed into an extremely small space. For many years, astronomers suspected the existence of this black hole based on the motions of stars near the galactic center. They observed some stars moving at extremely high speeds, up to a few percent of the speed of light, on elliptical orbits around a central point that appeared to contain nothing visible. By tracking the motions of these stars over many years, even decades, they could calculate the mass of the invisible object at the center, and the results pointed to a supermassive black hole. One of the most studied stars is S2, sometimes called S02. This star orbits SGRA star on an orbit with a period of only 16 years, and at its closest approach, it reaches a speed of about 2.5% of the speed of light, roughly 7,500 kilometers per second. Observations of this star provided the strongest evidence for the supermassive black hole, and this work led to the 2020 Nobel Prize in Physics for astronomers Reinhard Genzel and Andrea Ghez. But the black hole cannot be seen directly in visible light, because nothing can escape from it. So how can we see it? The answer is through radio emission. Matter falling toward a black hole does not fall straight in, but spirals around it in an accretion disk. And in the process, it is heated to extremely high temperatures and emits radiation at many wavelengths, including radio waves. In 2019, an international project called the Event Horizon Telescope, using a network of radio telescopes around the world to create an Earth-sized virtual telescope, released the first image of a black hole, not of SGRA star, but of the black hole at the center of the galaxy M87, about 54 million light-years away. That image showed a ring of light surrounding a dark region, exactly as Einstein's general relativity predicted. In May 2022, the Event Horizon Telescope team also released the first image of Sagittarius A star, the black hole at the center of our galaxy. Although the image is somewhat blurred and difficult to interpret due to the distance and the variability of the surrounding material, it remains an extraordinary scientific achievement, the first time we have seen the dark heart of our galaxy. SGR. A star is not a highly active black hole. It is relatively quiet compared with some supermassive black holes in other galaxies that are devouring large amounts of matter and emitting powerful radiation. But occasionally, it does flare, times when infalling material emits X-rays or gamma rays. Scientists believe that in the past, SGR, a star, may have been much more active, and it could become active again in the future if more material falls in. Looking at images of other spiral galaxies, we see that many of them have a bar-shaped structure across their nucleus, and the spiral arms often begin at the ends of that bar. Such galaxies are called barred spiral galaxies, as opposed to ordinary spiral galaxies without a bar. The Milky Way is a barred spiral galaxy. The central bar of the Milky Way is about 27,000 light-years long, stretching from one side of the galaxy to the other, and passing through the center where Sagittarius A star sits. It is not perfectly straight, but slightly curved and twisted, and it rotates at a pattern speed different from the rotation of the surrounding galactic disk. This bar plays an important role in the structure and evolution of the galaxy. It acts like a pump, moving gas and stars from the disk into the central regions, feeding the supermassive black hole and fueling star formation in the central area. At the same time, it generates complex orbital patterns and resonances that cause some stars and gas to concentrate into rings and spiral features. But the story is more complicated. Some recent studies suggest the Milky Way may have not just one bar, but two. There could be a smaller bar within the larger bar, a nested structure rotating at a different speed. The idea of a bar within a bar is still debated and requires more observations to confirm. But if true, it would make the Milky Way's structure far more complex than previously thought. The formation of bars in galaxies is a natural process that arises from gravitational instabilities. As a galactic disk rotates, any small perturbation in the mass distribution can be amplified by gravity, forming more organized structures. The bar is one such structure, a product of self-organization in a many-body system. Computer simulations show that many spiral galaxies, if not all, will develop bars at some point in their history, and these bars can persist for billions of years or dissolve and reform depending on conditions. The Milky Way's disk is not a homogeneous structure. It actually consists of two main components, the thin disk and the thick disk. These two components differ in thickness, in composition, in the ages of their stars, and in their motions. The thin disk is the component we usually think of when we talk about the galactic disk. It has a thickness of about 1,000 light-years, contains most of the galaxy's gas and dust, and is where most new stars are being born. Stars in the thin disk are relatively young, with average ages of a few billion years, and they are metal-rich, meaning they contain many elements heavier than hydrogen and helium. These stars move on nearly circular orbits around the galactic center with relatively uniform speeds. The thick disk, by contrast, is an older and thicker component with a thickness of about 3,000 light-years. It contains older stars with average ages of about 10 billion years, and these stars are more metal-poor than those in the thin disk. They move on orbits with higher inclinations and greater ellipticity, producing a thicker spatial distribution. The thick disk contains almost no gas and dust, and therefore very few new stars are forming there. The existence of these two disk components tells us about the Milky Way's formation history. The thick disk is thought to have formed earlier, during the galaxy's turbulent youth, when many collisions and mergers with smaller galaxies still occurred. These collisions stirred stellar orbits, producing a thicker spatial distribution and large random motions. Later, as the galaxy settled, gas and dust cooled and settled into a thinner disk where new stars formed on more circular and orderly orbits. The Sun, at about 4.5 billion years old, belongs to the thin disk. It is a younger generation star, born from gas that had been enriched by many earlier generations of stars. The Sun's chemical composition reflects this, with about 2% of its mass made up of elements heavier than hydrogen and helium, elements produced in the cores of ancient stars and in supernova explosions. Studies of the thin and thick disks help astronomers better understand the formation and evolution of galaxies in general. They show that a galaxy does not form once and then remain static, but undergoes a long, complex process with many stages. Each generation of stars tells a story, and by studying stars of different ages and locations, we can reconstruct the galaxy's history, much like archaeologists reconstruct the history of a civilization from artifacts and fossils. We mentioned this briefly before, but it is worth exploring further. The solar system does not move in a perfect flat circle around the galactic center. Instead, it oscillates up and down through the central plane of the galactic disk, like a rocking horse on a carousel, moving up and down while circling. This oscillation cycle takes about 60 to 70 million years to complete a full cycle from above the plane to below and back again. The amplitude of the oscillation, the farthest distance we move above or below the plane, is about 300 light-years. Currently, we are about 70 light-years above the galactic plane and moving back toward the plane. The cause of this oscillation is the gravitational pull from the mass distributed in the galactic disk. When the solar system moves above the plane, the mass of the disk below pulls it back. When it moves below, the mass above pulls it back. It is a form of harmonic oscillation, like a pendulum or a spring, but on a cosmic scale. This oscillation may have interesting consequences for Earth and life on it. Each time we pass through the galactic plane, where the density of stars, gas, and dust is highest, we increase the likelihood of encountering phenomena that could affect the solar system. For example, when passing through the plane, we are more likely to encounter giant molecular clouds, dense collections of gas and dust that can contain millions of solar masses. If the solar system passes through or near such a cloud, its gravity could perturb the Oort cloud, the reservoir of trillions of comets at the edge of the solar system, sending some toward the inner solar system and increasing the chance of impacts with Earth. Furthermore, when near the galactic plane, we are also closer to massive stars and star-forming regions where many supernovae occur. A nearby supernova could emit enough radiation to affect Earth's atmosphere, especially the ozone layer that shields us from ultraviolet radiation from the sun. Some scientists have proposed that the solar system's oscillation through the galactic plane may correlate with cycles of mass extinctions on Earth occurring about every 26 to 30 million years. However, this hypothesis remains controversial. The data on extinction cycles are not entirely clear, and many other factors could explain them, from volcanic activity and climate change to asteroid impacts. But the idea that our position in the galaxy can influence life on Earth is an intriguing one, reminding us that we do not exist in isolation, but are part of a vast and complex cosmic system. So we have traveled a long way through the structure and motions of the Milky Way. We have seen that even while lying still in the comfortable space around you, you are moving at an incredible speed through the universe, orbiting the galactic center in a journey that takes hundreds of millions of years to complete. We have seen that the solar system resides in a relatively quiet region of the galaxy, a small spur between the major arms, and that this location may be one of the fortunate factors enabling life to develop on Earth. We have looked into the dark heart of the galaxy, where a supermassive black hole lies in wait, devouring what comes near it. We have explored the galaxy's complex structure, from the central bar to the two-tiered disk, with different generations of stars, from the solar system's oscillation through the galactic plane to the potential impacts of these motions on life on our planet. All of this reminds us that the universe is not a static picture, but a living image that is always in motion and always changing. Every star, every planet, every cloud of gas moves along complex orbits governed by gravity, by the laws of physics, and by the billions of years history of the cosmos. And we, small beings on a small planet, are also part of this grand dance. We are moving with everything else, spinning in a vast cosmic machine that never stops. And although we do not feel these motions in daily life and believe ourselves to be standing still on solid ground, the truth is we are hurtling through space at terrifying speeds on a journey with no final destination. Only endless revolutions in the darkness of the cosmos. It is an eternal cycle, a loop without beginning or end, only constant transformation. And while you lie here in this quiet moment, you are part of that cycle, a single note in the cosmic symphony, a small ripple on the ocean of time. Imagine watching a ballet dancer spinning on stage. You can see the dancer. You can see the ornate costume. You can see the stage lights. But what keeps that dancer from falling? What keeps them balanced in those rapid spins? It is the muscles you cannot see beneath the costume, the skeleton you cannot see beneath the skin, the invisible but essential structures. Dark matter is the invisible structure of the Milky Way. It does not emit light, absorb light, or reflect light. It is completely transparent to every form of electromagnetic radiation we know, from radio waves to gamma rays. It does not interact with normal matter except through a single force, gravity, and therefore we know of its existence only through its gravitational effects on the things we can see. The story of the discovery of dark matter begins in the 1930s when a Swiss astronomer named Fritz Zwicky was studying the motions of galaxies in a cluster called the Coma cluster. He found that the galaxies in that cluster were moving too fast to be explained by the visible mass alone. According to Newton's laws, if they move so fast, they should fly apart from the cluster and disperse into space. But they did not disperse. They remained bound together by gravity. This meant there had to be more mass than what we could see, some invisible mass holding the cluster together. Zwicky called this mysterious mass Dunkle Materie, which in German means dark matter. But his idea was not widely accepted by the scientific community at that time because it seemed too strange and too unbelievable. It was not until the 1970s, when American astronomer Vera Rubin and her colleagues studied the rotation curves of spiral galaxies, that the evidence for dark matter became essentially indisputable. Rubin measured the rotation speeds of stars at different distances from the galactic center. According to Kepler's laws, rotational speed should decrease with distance from the center, just as planets farther from the sun move more slowly than those nearer in. What Rubin found was completely different. The rotation speeds of stars at a galaxy's edge remain nearly constant, even at very large distances where almost no visible stars remain. This was a major anomaly, and the only way to explain it was to posit a large amount of invisible mass surrounding the galaxy, a gigantic halo of dark matter extending far beyond the visible stellar disk. In the Milky Way, scientists estimate that dark matter accounts for about 85% of the total mass, while ordinary matter, the stuff that makes up stars, planets, gas, dust, and us, makes up only about 15%. That is an astonishing ratio. It means most of our galaxy is invisible and cannot be detected directly by any telescope at any wavelength. Dark matter forms a roughly spherical halo around the Milky Way, extending far beyond the stellar disk. This halo may have a diameter of up to 600,000 light-years or more, about 6 times the size of the visible stellar disk. Within this halo, dark matter is distributed unevenly, with denser and sparser regions, producing a complex structure that we can study only through computer simulations and indirect observations. But what is dark matter? That is one of the biggest questions in modern physics. We know it is not ordinary matter. It is not made of protons, neutrons, electrons, or any particle in the standard model of particle physics. There are many competing theories about the nature of dark matter. One popular hypothesis is that it consists of particles not yet detected called WIMPs, which stands for Weakly Interacting Massive Particles. Particles with large mass that interact very weakly with ordinary matter. Another hypothesis invokes actions, extremely light particles proposed to solve a different problem in particle physics. To date, despite dozens of experiments around the world attempting to detect dark matter directly, we have not found any definitive signs. Dark matter remains a mystery, a phenomenon we know must exist because of its gravitational effects, yet we do not know what it is. This is a humble reminder that although we understand much about the universe, there is still a great deal we do not know, and many mysteries yet to be solved. Let us delve a little deeper into the evidence for dark matter that I just mentioned. The rotation curve of a galaxy is one of the most powerful and intuitive pieces of evidence for dark matter, and it is worth spending time to understand it. When an object orbits around a central mass, its orbital speed depends on two main factors: the distance from the center and the mass enclosed within its orbit. This is Kepler's law, discovered more than 400 years ago while studying the motions of planets around the Sun. According to this law, planets closer to the Sun move faster than those farther away. Mercury, the planet nearest the Sun, takes only 88 days to complete one orbit, while Neptune, the farthest known planet in the classical solar system, takes about 160 years. If all a galaxy's mass were concentrated at the center, we would expect a similar pattern. Stars near the galactic center should rotate faster, and as distance increases, rotation speed should decline according to a specific mathematical formula. But reality is not like that. When Vera Rubin and her colleagues measured the rotation speeds of stars in many different galaxies, they found that the rotation speed does not fall off with distance from the center. Instead, it remains nearly flat, meaning stars at the galaxy's edge rotate at speeds similar to those of stars much closer to the center. This can only be explained if there is additional mass in the outer regions, mass we cannot see. And not just a little extra mass, but a great deal more than all the visible stars and gas combined. The distribution of this invisible mass must extend far beyond the visible matter, forming a colossal halo around the galaxy. In the Milky Way, the rotation curve shows a similar pattern. Stars at distances of 30,000, 40,000, even 50,000 light-years from the center still orbit at roughly 200 to 250 kilometers per second, nearly unchanged from closer distances. This tells us that the Milky Way's dark matter halo must extend at least to those distances, and likely much farther. A helpful analogy is to imagine the Milky Way as an orange floating in a large bowl of water. The orange, with its bright peel and sweet flesh, represents the visible part of the galaxy: the stars, gas, and dust. The bowl of water, transparent and invisible, represents the dark matter halo. The bowl is much larger than the orange, perhaps 10 times the volume, and contains far more mass, maybe 5 to 6 times as much. We can only see the orange, but it is the bowl of water that occupies most of the space and mass. Understanding this has completely changed the way we think about galaxies. Before the discovery of dark matter, we thought of a galaxy primarily as a collection of stars with some gas and dust mixed in. Now, we know a galaxy is dominated by dark matter, and the stars are like tiny specks suspended in an invisible ocean. This is a complete reversal of perspective. like realizing that what you thought was reality is only the surface, and that most of the substance lies hidden beneath. When we think of the Milky Way, we often picture a flat disk with spiral arms where the sun and most of the stars, visible to the naked eye, reside. But the disk is only a small part of the galaxy. Most of the Milky Way's mass and volume lie in the halo, a spherical region surrounding the disk and extending far beyond it. The galactic halo is not entirely empty space. Although its density is very low compared to the disk, it contains several interesting components. First and foremost, it contains most of the galaxy's dark matter, as we have discussed. But in addition to dark matter, the halo also contains ordinary matter, though in much smaller amounts. One of the most notable components of the halo is its globular clusters. These are spherical collections of hundreds of thousands to millions of stars tightly bound together in a relatively small volume, typically only a few dozen to a few hundred light-years across. Globular clusters are among the oldest structures in the galaxy, with ages usually between 10 and 13 billion years, nearly as old as the universe itself. They formed in the galaxy's early epochs, when dense gas and favorable conditions allowed for intense episodes of star formation. The Milky Way has about 150 to 200 confirmed globular clusters, although there may be more hidden by dust or too faint to detect. These clusters orbit the galactic center on highly elliptical and inclined paths, sometimes passing through the disk and sometimes reaching high into the halo. They are like faithful satellites, ancient companions that have witnessed the galaxy's entire history. Studying globular clusters teaches us much about the galaxy's past. Because the stars in a cluster formed at the same time from the same gas cloud, they share a common age and initial chemical composition. By studying stars in these clusters, we can determine the cluster's age and thereby set a lower bound on the galaxy's age. We can also study their chemical makeup to learn about conditions in the early universe when these clusters formed. Beyond globular clusters, the halo also contains individual stars, lone stars not bound to any cluster that wander through the vast space. These halo stars are often very old and metal-poor, suggesting they formed in the galaxy's early stages. Some may be the remnants of globular clusters that have dissolved over time due to gravitational interactions. Others may have come from dwarf galaxies the Milky Way swallowed long ago, and now their stars drift in the halo like refugees from lost worlds. In fact, one of the ways astronomers study the Milky Way's merger history is by searching for stellar streams in the halo, groups of stars with similar motions and chemical compositions that suggest they once belonged to the same dwarf galaxy. Many such stellar streams have been discovered, each telling the story of an ancient collision, a merger that occurred billions of years ago, but still leaves traces today. The halo also contains a small amount of hot gas at temperatures of millions of degrees called the galactic corona. This gas is too hot to emit visible light, but it emits X-rays and can be observed with spaceborne X-ray telescopes. The corona is heated by various processes, including supernovae, stellar winds, and possibly the infall of gas from the intergalactic medium. It acts as a reservoir of heat, storing energy from violent activity in the disk and slowly releasing it into space. All of these components, from the dominant dark matter to ancient globular clusters, lone drifting stars, and the hot gas corona, together make up the galactic halo, a vast and complex region that we are only beginning to understand. The halo is not an empty or meaningless region, but an important part of the galaxy that contains much of its mass and history. And now, having explored the invisible and hidden components of the Milky Way, take a moment to reflect on this. Around you, right now, there are dark matter particles passing through your body, through this room, and through the Earth without leaving any trace. They do not touch you or interact with your atoms, but they are there, an invisible flow, an essential component of the universe we inhabit. Above us, in the night sky, if we could look far enough, we would see ancient globular clusters suspended in the halo, bright spheres containing millions of stars, silent witnesses to the galaxy's entire history. They were here before the sun was born, before the earth formed, and they will remain long after we are gone. It is a humbling thought, and also an astonishing one. We live in a universe that is largely invisible, a universe where what we see is only a small part of the whole. And although we do not yet understand everything, and many mysteries remain unsolved, each advance in our knowledge opens new questions and new realms to explore. Let these thoughts settle gently, like snowflakes falling in a quiet night. Feel the connection between you and these mysteries, between the visible and the invisible, between light and darkness. All are part of the same reality, the same wondrous universe we strive to understand. Now breathe deeply and join me in continuing to explore other invisible phenomena of the Milky Way, things that are happening right now but lie entirely beyond our direct sight and perception. Right now, as you lie here in the quiet, trillions of particles are passing through your body every second. They come from the sun, from distant stars, from supernova explosions that happened thousands of years ago, and even from galaxies at the edge of the observable universe. You do not feel them, see them, or hear them, but they are there, an endless flow of invisible energy and matter. These particles come in many varieties. First are cosmic rays, which are not really rays, but charged particles moving at speeds close to the speed of light. Most cosmic rays are protons, the nuclei of hydrogen atoms, but some are nuclei of heavier elements, such as helium, carbon, or even iron. They are produced by many sources, but the primary sources are supernovae, the final explosions of massive stars. When a massive star runs out of fuel and collapses, its core compresses into an extremely dense object, and the outer layers are ejected at speeds of up to a few percent of the speed of light. In that explosion, a huge amount of energy is released, and part of that energy is transferred to particles, accelerating them to very high speeds. These particles stream away from the explosion and travel through the galaxy, bent by cosmic magnetic fields, scattered by clouds of gas, and eventually, some reach the Earth. When cosmic rays collide with the Earth's atmosphere, they create a cascade of reactions, producing secondary particles such as muons pions and electrons. Those secondary particles continue to fall, and some reach the surface of the Earth, even passing through buildings and through our bodies. Every second, on the order of a few hundred to a few thousand muons from cosmic rays pass through an average person, depending on altitude and geographic location. These particles carry a small amount of ionizing radiation that can cause some damage to DNA in cells. This is one of the natural background radiation sources we face daily, along with radiation from radioactive elements in the ground and rocks, and from direct cosmic radiation. The total dose from cosmic rays is small compared with other sources such as medical X-rays or natural radon radiation, but it remains an unavoidable part of life on this planet. But cosmic rays are not the only particles that pass through us. There are also neutrinos, far stranger and more mysterious particles. Neutrinos are extremely light, electrically neutral particles that interact very weakly with matter. They are produced in many nuclear processes, including the nuclear reactions in the sun's core, radioactive decay, and supernova explosions. Every second, about 60 billion solar neutrinos pass through each square centimeter on Earth. That is an almost unimaginable number. If you hold up your hand for 1 second, trillions of neutrinos will pass through it, and most of them do not interact with anything. They pass through the Earth as if it were not there, like a thin mist. The probability of a neutrino interacting with an atom in your body is extremely small. Perhaps only 1 in hundreds of trillions of neutrinos will collide with any atom. To detect neutrinos, scientists build enormous detectors, usually placed deep underground or under the ocean to shield them from cosmic ray backgrounds. These detectors contain thousands of tons of water or other fluids and wait for a rare neutrino to interact with an atom, producing a faint flash of light that sensitive sensors can detect. Even with such enormous detectors, they detect only a few dozen or a few hundred solar neutrinos per day, and even fewer from more distant sources. Neutrinos play an important role in the universe. In a supernova explosion, most of the energy, about 99%, is carried away by neutrinos rather than by light or matter. Neutrinos stream out from the explosion at nearly the speed of light, arriving before the shock wave breaks the star's outer layers and produces visible light. Therefore, by detecting neutrinos from a supernova, astronomers can receive an early warning hours before the light arrives, allowing them to point telescopes at the right location to observe the explosion from the very beginning. In 1987, when supernova SN 1987A exploded in the Large Magellanic Cloud, neutrino detectors on Earth recorded a few dozen neutrinos from the explosion, hours before the visible light arrived. That was the first time neutrinos from a supernova were detected, and it confirmed many theories about how stars die and how neutrinos carry away energy. So, right now, as you rest, an invisible universe is happening around and through you. Cosmic rays from distant supernovae and neutrinos from the sun and other sources in the galaxy are passing through you every second, a continuous flow of energy and matter you do not perceive. This is a reminder that reality is far more complex than what we can sense directly, and that science allows us to uncover the hidden layers of this reality. Take a moment to reflect on this. We live in a world that is mostly invisible. Dark matter accounts for 85% of the galaxy's mass, yet we cannot see it or touch it. Cosmic rays and neutrinos pass through us every second, yet we do not feel them. Magnetic fields and gravitational waves ripple through space, bending time and space, yet we do not perceive them. In fact, one of the ways astronomers study the Milky Way's merger history is by searching for stellar streams in the halo. Groups of stars with similar motions and chemical compositions that suggest they once belonged to the same dwarf galaxy. Many such stellar streams have been discovered, each one telling the story of an ancient collision, a merger that occurred billions of years ago, but still leaves traces today. The halo also contains a small amount of hot gas, at temperatures of millions of degrees, called the galactic corona. This gas is too hot to emit visible light, but it emits X-rays and can be observed with spaceborne X-ray telescopes. The corona is heated by several processes, including supernovae, stellar winds, and possibly the infall of gas from the intergalactic medium. It acts as a reservoir of heat, storing energy from violent activity in the disk and slowly releasing it into space. All of these components, from the dominant dark matter to ancient globular clusters, lone drifting stars, and the hot gas corona, together form the galactic halo, a vast and complex region that we are only beginning to understand. The halo is not an empty or meaningless region, but an important part of the galaxy that contains much of its mass and history. And now, having explored the invisible and hidden components of the Milky Way, take a moment to reflect on this. Around you, right now, dark matter particles are passing through your body, through this room, and through the earth without leaving any trace. They do not touch you or interact with your atoms, but they are there, an invisible flow, an essential component of the universe we inhabit. Above us, in the night sky, if we could look far enough, we would see ancient globular clusters suspended in the halo, bright spheres containing millions of stars, silent witnesses to the galaxy's entire history. They were here before the sun was born, before the earth formed, and they will remain long after we are gone. It is a humbling thought, and also an astonishing one. We live in a universe that is largely invisible, a universe where what we see is only a small part of the whole. And although we do not yet understand everything, and many mysteries remain unsolved, each advance in our knowledge opens new questions and new realms to explore. Let these thoughts settle gently, like snowflakes falling on a quiet night. Feel the connection between you and these mysteries, between the visible and the invisible, between light and darkness. All are part of the same reality, the same wondrous universe we strive to understand. Now breathe deeply and join me in continuing to explore other invisible phenomena of the Milky Way, things that are happening right now but lie entirely beyond our direct sight and perception. Right now, as you lie here in the quiet, trillions of particles are passing through your body every second. They come from the sun, from distant stars, from supernova explosions that happened thousands of years ago, and even from galaxies at the edge of the observable universe. You do not feel them, see them, or hear them, but they are there. an endless flow of invisible energy and matter. These particles come in many varieties. First are cosmic rays, which are not really rays, but charged particles moving at speeds close to the speed of light. Most cosmic rays are protons, the nuclei of hydrogen atoms, but some are nuclei of heavier elements such as helium, carbon, or even iron. They are produced by many sources, but the primary sources are supernovae, the final explosions of massive stars. When a massive star runs out of fuel and collapses, its core compresses into an extremely dense object, and the outer layers are ejected at speeds of up to a few percent of the speed of light. In that explosion, a huge amount of energy is released, and part of that energy is transferred to particles, accelerating them to very high speeds. These particles stream away from the explosion and travel through the galaxy, bent by cosmic magnetic fields, scattered by clouds of gas, and eventually some reach the Earth. When cosmic rays collide with the Earth's atmosphere, they create a cascade of reactions, producing secondary particles such as muons, pions, and electrons. Those secondary particles continue to fall, and some reach the surface of the Earth, even passing through buildings and through our bodies. Every second, on the order of a few hundred to a few thousand muons from cosmic rays pass through an average person, depending on altitude and geographic location. These particles carry a small amount of ionizing radiation that can cause some damage to DNA in cells. This is one of the natural background radiation sources we face daily, along with radiation from radioactive elements in the ground and rocks, and from direct cosmic radiation. The total dose from cosmic rays is small compared with other sources such as medical X-rays or natural radon radiation, but it remains an unavoidable part of life on this planet. But cosmic rays are not the only particles that pass through us. There are also neutrinos, far stranger and more mysterious particles. Neutrinos are extremely light, electrically neutral particles that interact very weakly with matter. They are produced in many nuclear processes, including the nuclear reactions in the sun's core, radioactive decay, and supernova explosions. Every second, about 60 billion solar neutrinos pass through each square centimeter on Earth. That is an almost unimaginable number. If you hold up your hand for 1 second, trillions of neutrinos will pass through it. And most of them do not interact with anything. They pass through the Earth as if it were not there, like a thin mist. The probability of a neutrino interacting with an atom in your body is extremely small. Perhaps only 1 in hundreds of trillions of neutrinos will collide with any atom. To detect neutrinos, scientists build enormous detectors, usually placed deep underground or under the ocean to shield them from cosmic ray backgrounds. These detectors contain thousands of tons of water or other fluids and wait for a rare neutrino to interact with an atom, producing a faint flash of light that sensitive sensors can detect. Even with such enormous detectors, they detect only a few dozen or a few hundred solar neutrinos per day, and even fewer from more distant sources. Neutrinos play an important role in the universe. In a supernova explosion, most of the energy, about 99%, is carried away by neutrinos rather than by light or matter. Neutrinos stream out from the explosion at nearly the speed of light, arriving before the shock wave breaks the star's outer layers and produces visible light. Therefore, by detecting neutrinos from a supernova, astronomers can receive an early warning hours before the light arrives, allowing them to point telescopes at the right location to observe the explosion from the very beginning. In 1987, when supernova SN 1987A exploded in the Large Magellanic Cloud, neutrino detectors on Earth recorded a few dozen neutrinos from the explosion hours before the visible light arrived. That was the first time neutrinos from a supernova were detected, and it confirmed many theories about how stars die and how neutrinos carry away energy. So right now, as you rest, an invisible universe is happening around and through you. Cosmic rays from distant supernovae and neutrinos from the sun and other sources in the galaxy are passing through you every second. A continuous flow of energy and matter you do not perceive. This is a reminder that reality is far more complex than what we can sense directly, and that science allows us to uncover the hidden layers of this reality. Take a moment to reflect on this. We live in a world that is mostly invisible. Dark matter accounts for 85% of the galaxy's mass, yet we cannot see it or touch it. Cosmic rays and neutrinos pass through us every second, yet we do not feel them. Magnetic fields and gravitational waves ripple through space, bending time and space, yet we do not perceive them. What we see with our eyes, what we sense with our faculties, is only a very small part of the whole. It is like looking into a dark room through a small crack in the door. You can see a part, but most of it remains hidden in darkness. Science is the tool that allows us to widen that crack, illuminate the dark corners, and discover what lies hidden. And each time we discover something new, we realize there is much more we do not know. Dark matter remains a mystery. We know it exists, but we do not know what it is. Dark energy, another component that accounts for about 70% of the universe's energy and is driving the accelerated expansion of the universe, is even more mysterious. We do not understand its nature. We do not understand why it exists, and we do not know where it will lead the universe. But that is the beauty of science. It does not offer final, absolute answers. Instead, it is a relentless journey of discovery, a continuous process of questioning, observing, experimenting, and learning. Each answer opens 10 new questions. Each discovery reveals 10 new mysteries. And that is how we make progress, step by step, discovery by discovery, toward deeper understanding of the universe and our place within it. All of this reminds us that reality is far larger, more complex, and far more wondrous than what we can perceive directly. We live in a layered universe where the visible and the invisible intertwine, where light and darkness coexist, and where each answer opens new mysteries. Every star is its own story, a journey from birth to maturation, to aging, and finally to death. And in the Milky Way, with its hundreds of billions of stars, we have hundreds of billions of stories unfolding simultaneously at different stages of the life cycle. One common misunderstanding about a galaxy's spiral arms is to think of them as rigid arms rotating around the center, with stars fixed to them like grains of sand on a spinning plate. But reality is far more complex and interesting. Spiral arms are not fixed physical structures, but density waves, regions where stars and gas are temporarily concentrated as they move through. Imagine a crowded highway during rush hour. Sometimes you see traffic jams where cars move more slowly and are more densely packed, but those jams are not fixed. They move along the road, and individual cars enter the jam, slow down, then exit and speed up again. The traffic jam is a phenomenon, not a physical object. A galaxy's spiral arms operate in a similar way. They are regions of higher density, but individual stars are not attached to the arm. Instead, they move on their own orbits around the galactic center, and when they pass through a spiral arm, they slow down slightly due to the increased gravitational pull from the higher density. That slowdown causes them to spend more time in the arm, creating the higher density, much like cars slowing in a traffic jam. This idea is called density wave theory, developed largely by C.C. Lin and Frank Hsu in the 1960s. According to this theory, spiral arms rotate at a certain pattern speed, and that speed is different from the rotation speed of individual stars. At certain distances from the galactic center, a star's speed matches the pattern speed, and at those locations, called corotation resonance regions, special effects can occur. One of the strongest pieces of evidence for density wave theory is the enhanced star formation in spiral arms. As gas moves into an arm, it encounters shock waves from the density wave, is compressed, and conditions become favorable for gravitational collapse and new star formation. Therefore, spiral arms are often brighter because they contain many young, hot, luminous stars along with glowing gas regions around them. But these young stars do not remain in the arm forever. After they are born, they continue moving on their orbits and eventually leave the arm and move into the interarm region. The most massive, hottest, and brightest stars live very short lives, perhaps only a few million years, so they die in or near the arm where they were born. But longer-lived, smaller stars like the Sun can live for billions of years and pass through many arms during their lifetimes. The Sun, at about 4.5 billion years old, has passed through many spiral arms during its history. Each time it crosses an arm, it may encounter higher stellar density, more radiation from young hot stars, and possibly more nearby supernovae. Some scientists have suggested that arm crossings could influence Earth's climate, or even life itself, although the evidence for this hypothesis remains weak and controversial. At present, the Sun is not located in a major arm, but in the Orion Spur, a smaller structure between two large arms. This may be a fortunate position because it means we are in a relatively quiet region with less violent activity than in the major arms. But in the future, as the Sun continues its orbit, it will move into and out of different arms, and the environment around the solar system will change. When we think of stars in the galaxy, we often imagine they all orbit in the same direction around the center, like planets orbiting the Sun. And indeed, most stars in the galactic disk do so, but not all. There are some stars that move in the opposite direction, and there are stars on highly inclined orbits that do not lie in the disk plane. These stars are often outsiders, atypical residents of the galaxy. Some of them may have come from dwarf galaxies the Milky Way swallowed in the past. When a dwarf galaxy is accreted, its stars do not automatically adjust their orbits to match the common motion of the new host galaxy. Instead, they retain much of their original velocities and directions, producing odd and atypical orbits. By studying these unusually moving stars, astronomers can reconstruct the Milky Way's merger history. They search for groups of stars with similar velocities and chemical compositions, suggesting they once belonged to the same dwarf galaxy. Many such stellar streams have been found in the Milky Way's halo, each stream a remnant of a dead galaxy, a world that has vanished but still leaves traces in its stars. A famous example is the Sagittarius stream, which we mentioned earlier. This is the remnant of the Sagittarius dwarf galaxy being torn apart by the Milky Way's tidal forces. Stars from that galaxy form a long stream around the Milky Way, and they have chemical compositions and motions distinct from the disk's native stars. Studying this stream has helped astronomers better understand galaxy mergers and the Milky Way's history. Besides stars from other galaxies, there are stars flung from their original positions by gravitational interactions. For example, when two stars in a binary system near the galactic center interact with the supermassive black hole, one star can be captured by the black hole while the other is ejected at extremely high speed. Or when a star passes through a dense star cluster, it can be scattered by many successive gravitational encounters, eventually being hurled away with a different speed and direction than it originally had. These interactions produce a diverse population of stellar orbits in the galaxy. While most disk stars have relatively circular orbits close to the disk plane, some have elliptical orbits, some have inclined orbits, and some even move in the opposite direction. This diversity tells us about the galaxy's complex history, about the interactions and collisions that have occurred, and about the complex dynamics of a many-body system on a galactic scale. Now, let us talk about a truly strange and impressive phenomenon: hypervelocity stars. These are stars moving at speeds high enough to escape the Milky Way's gravitational pull, flying into intergalactic space and never returning. To escape the Milky Way from our location, an object needs to reach an escape velocity of about 500 to 600 kilometers per second. That is nearly 3 times the typical rotation speed of stars in the disk. How can a star reach such a high speed? The most common mechanism is interaction with the supermassive black hole at the galactic center. Imagine a binary star system, 2 stars orbiting each other, approaching too close to the galactic center. When they come near the black hole, the extreme tidal forces can tear the binary apart. One star may be captured by the black hole, falling into an orbit around it, or even being swallowed. Meanwhile, the other star receives a massive velocity kick from the interaction, like a slingshot effect, and is ejected with speeds that can reach 1,000 kilometers per second or more. The first hypervelocity star was discovered in 2005 by astronomer Warren Brown and colleagues. This star, named SDSSJ 090745.0 plus 024507, is moving at about 850 kilometers per second relative to the Milky Way, enough to escape the galaxy. Analysis of its trajectory suggests it may have been ejected from the galactic center roughly 80 million years ago. Since then, dozens of other hypervelocity stars have been discovered, and that number continues to grow as sky surveys become more precise and comprehensive. Some of these stars have origins that clearly point to the galactic center, confirming the hypothesis of interactions with the supermassive black hole. But others have trajectories that do not point to the galactic center, suggesting there may be alternative mechanisms that produce them. One alternative mechanism is interactions between two binary star systems. If two binary systems encounter one another in a dense star cluster, a complex gravitational interaction can occur, and in some rare cases, one of the stars can be ejected at very high speed. Or, if a star in a binary system becomes a supernova, the explosion can be asymmetric and the remaining star can receive a velocity kick, although usually not enough to escape the galaxy, but enough to produce an unusual orbit. Hypervelocity stars are fascinating objects to study for several reasons. First, they provide direct evidence for the existence and influence of the supermassive black hole at the galactic center. Second, by studying their trajectories, we can learn about the mass distribution in the galaxy, including the distribution of dark matter. Third, they raise intriguing questions about the fate of any planets that might orbit these stars. If a hypervelocity star has planets, would those planets survive the enormous velocity kick? And if they do, they would be on a solitary journey out of the galaxy into intergalactic space, where nothing exists but darkness and vast distances. If we look at the Milky Way's history, we see that the star formation rate has changed significantly over time. In the distant past, when the galaxy was young and full of primordial gas, the star formation rate was very high. Billions of stars were born in a relatively short time, consuming gas rapidly. But over time, as more gas was converted into stars, and as some gas was driven out of the galaxy by stellar winds and supernovae, the star formation rate began to decline. Today, the Milky Way produces about 1 to 3 solar masses of new stars per year, compared with perhaps 10 to 15 solar masses per year at its peak roughly 10 billion years ago. This decline does not mean the galaxy is dying. It is simply maturing and entering a more stable phase of its life. Astronomers sometimes call this the galaxy's middle age. Like a middle-aged person who no longer grows as rapidly as in youth, but remains healthy and active, the Milky Way continues to form new stars, but at a slower and more sustainable rate. However, this decline is not uniform across the galaxy. Some regions remain very active in star formation, especially in the spiral arms and in certain areas near the center. These regions contain giant molecular clouds, dense and cold hydrogen gas complexes where conditions favor gravitational collapse and star formation. One of the most famous star-forming regions in the Milky Way is the Orion Nebula, about 1,300 light-years away. It is the closest star-forming region to Earth that we can see with the naked eye, appearing as a faint patch in Orion's sword. Inside this nebula, thousands of new stars are forming, from massive, hot, luminous stars to smaller stars similar to the Sun. Observing the Orion Nebula gives us a view of how the Sun and the solar system may have formed about 4.5 billion years ago. But not all the gas in the galaxy participates in star formation. A significant fraction of the gas is heated to temperatures too high to collapse and form stars. This energy comes from many sources: radiation from young, hot stars, powerful stellar winds blowing from the surfaces of massive stars, and especially supernova explosions. Each supernova releases an enormous amount of energy, heating and blowing away surrounding gas, creating hot bubbles that can extend for hundreds of light years. These bubbles prevent gas from collapsing and forming new stars, at least temporarily. But eventually, after millions of years, the gas cools, contracts, and star formation can resume. It is a continuous cycle. Stars form from gas. Stars live and shine. Stars die and return energy and material to the gas. And the cycle repeats. Astronomers call this the galactic recycling cycle, a fundamental process that sustains the galaxy over billions of years. When stars form, they usually do not form singly, but in groups, in star clusters. This happens because the molecular clouds where stars form are often large enough to produce hundreds or thousands of stars at once. These stars, born from the same cloud, share the same age and initial chemical composition, and they begin their lives close together in space. There are two main types of star clusters: open clusters and globular clusters. Open clusters are loose groupings of a few dozen to a few thousand stars, typically located in the galactic disk, and relatively young, with ages ranging from a few million to a few billion years. Globular clusters, as we discussed earlier, are much denser groupings of hundreds of thousands to millions of stars, usually located in the halo and very old, with ages between 10 and 13 billion years. But neither open clusters nor globular clusters are permanently stable. Over time, they can dissolve, and their member stars can disperse into the larger galaxy. This happens through several processes. The first is evaporation, a process in which stars gradually gain enough energy to escape the cluster's gravitational pull. This occurs through many small gravitational encounters among stars in the cluster. Each time two stars pass near each other, they exchange energy and velocity. Sometimes a star gains enough energy to leave the cluster, while another loses energy and sinks deeper into the cluster. Over millions or billions of years, this process can cause the cluster to lose members and eventually dissolve entirely. The second process is tidal forces from the galaxy. As a cluster orbits the galactic center, it experiences tidal forces from the galaxy's non-uniform gravitational field. The part of the cluster closer to the galactic center feels a stronger pull than the farther part, producing a stretching force. If this tidal force is strong enough, it can overcome the cluster's self-gravity, and the cluster will be stretched and disrupted. This process is especially potent for clusters that pass near the galactic center or cross the disk, where the mass density is higher. Each such passage is a challenge to the cluster's survival, and over time, these passages can accumulate and lead to complete dissolution. The third process is interactions with giant molecular clouds. When a cluster passes through such a cloud, the cloud's gravity can perturb the cluster and unbind some of its stars. If a cluster passes through many clouds during its lifetime, the cumulative effect can be significant. Because of all these processes, most open clusters have relatively short lifetimes, often only a few 100 million to a few billion years before they fully dissolve. Globular clusters, thanks to their much larger masses and stronger gravity, can survive much longer, but even they are not immortal. Some globular clusters have been destroyed in the past by interactions with the galaxy, and their stars now drift freely in the halo. Our Sun is a perfect example of a star that was once a member of a cluster, but is now solitary. When the Sun formed about 4.5 billion years ago, it did not form alone, but perhaps with a few thousand other stars in an open cluster. But that cluster dissolved long ago, and the Sun's sibling stars are now scattered across the galaxy on different orbits. Astronomers have tried to find these sibling stars by analyzing the chemical compositions and motions of millions of stars. The idea is that stars born from the same cloud will have very similar chemical fingerprints, and by tracing their orbits backward in time, one can identify which stars were once near each other. A few candidates have been proposed, but definitive confirmation remains challenging because of the huge number of stars and uncertainties in measurements. We briefly mentioned extremely metal-poor stars earlier, but they deserve deeper exploration because of their great scientific significance. These stars are living fossils, windows into an era of the universe that we cannot observe directly by other means. In the early universe, after the Big Bang, only 3 elements were produced: hydrogen, about 75% by mass; helium, about 25%, and a very small amount of lithium. All other elements, from carbon and oxygen to iron and gold, were produced later inside stars via nuclear fusion and in supernova explosions. The first generation of stars, called population 3 stars, formed from this primordial gas, almost entirely hydrogen and helium. These stars are thought to have been very massive, perhaps up to a few 100 times the mass of the Sun, lived very briefly, and died in powerful supernova explosions. To date, we have not observed any population 3 stars directly, but we believe they must have existed to account for the presence of heavy elements in later stars. By studying extremely metal-poor stars, astronomers can learn about conditions in the early universe and about the chemical enrichment history of the galaxy. One interesting finding is that some of these stars show unusual elemental ratios, suggesting they were enriched by only one or a few individual supernova rather than by a well-mixed mixture of many supernova. So we have completed our journey through the world of stars. Each star is its own story, from birth to death, and among the Milky Way's hundreds of billions of stars, all those stories are unfolding simultaneously. Let these thoughts settle, and join me as we shift our focus to other, less conspicuous, but equally important components of the galaxy: gas and dust. These components may not shine like stars, but they are the raw material, from which stars are born. The legacy stars leave when they die, and the environment where the galaxy's physical and chemical processes occur. If stars are the bright cities in the night, then gas and dust are the vast fields around them, fertile lands where new life can sprout, and quiet graveyards where the dead are recycled. Space between the stars is not the complete void many people imagine. Instead, there is a large amount of gas, mainly hydrogen, with a bit of helium and other elements. This gas has a very low density by Earth standards, often only a few atoms per cubic centimeter, but given the enormous volume of interstellar space, the total mass of the gas is substantial, accounting for about 10 to 15% of the ordinary matter mass in the galaxy. This gas is not distributed uniformly, but concentrates into clouds of different sizes and properties. The largest and densest of these clouds are called giant molecular clouds. These clouds can contain anywhere from hundreds of thousands to millions of times the mass of the Sun and can extend for hundreds of light years. They are the largest structures in the galaxy in terms of ordinary matter. Inside these clouds, the temperature is very low, typically only 10 to 20 degrees above absolute zero. That is negative 250 degrees Celsius. At these cold temperatures, hydrogen atoms pair up to form molecular hydrogen, H2, and other molecules can form as well, such as carbon monoxide CO, water H2O, ammonia NH3, and many other complex molecules. That is why they are called molecular clouds. These clouds are the birthplaces of stars. When a part of a cloud becomes dense enough, gravity can overcome the gas pressure and the cloud begins to collapse. This collapse is not uniform, but fragments, producing many dense cores, each of which can become a star, or a binary or multiple star system. This process takes millions of years, and the result is the formation of a new star cluster. One of the most famous giant molecular clouds we know is the Orion molecular cloud, located behind the Orion Nebula that we can see with the naked eye. This cloud contains enough material to form tens of thousands of stars, and star formation is still ongoing within it. Observing this cloud with infrared and radio telescopes has given us deep insight into how stars are born. But not all the gas in a molecular cloud becomes stars. Only a small fraction, perhaps a few percent, actually collapses and forms stars. The remainder is blown away by winds from the newly formed stars and by supernova explosions of massive stars that die early. These processes disrupt the cloud, ending star formation there, and return the gas to the interstellar medium where it can be recycled to form new generations of stars in the future. Not all gas clouds in the galaxy are actively forming stars. There are clouds called quiescent clouds that have not yet begun the collapse process to form stars, even though they may have enough mass and density to do so. This raises an interesting question. Why do some clouds form stars, while others do not? The answer lies in a delicate balance among many forces. For a cloud to collapse and form stars, gravity must overcome the forces that resist collapse, including thermal pressure from the random motions of molecules, magnetic pressure from magnetic fields threading the cloud, and turbulent motions within the cloud. If these opposing forces are strong enough, the cloud may be stable and not collapse, at least temporarily. Astronomers use a criterion called the Jeans criterion to determine whether a cloud can collapse. This criterion, developed by the English physicist James Jeans in the early 20th century, compares the cloud's gravitational energy to its thermal energy. If a cloud is large enough and cold enough, it becomes unstable and begins to collapse. But if it is too small or too hot, it remains stable. However, the simple Jeans criterion is not always sufficient to explain everything. Other factors, such as magnetic fields and turbulence, also play important roles. Magnetic fields can provide additional pressure against collapse, while turbulence can create denser regions where collapse is more likely. Understanding all these factors and how they interact is one of modern astronomy's great challenges. Studying quiescent clouds can help us understand what triggers star formation. It may be an external event, such as a shock wave from a nearby supernova, a collision with another cloud, or passage through a spiral arm of the galaxy. These events can compress a cloud enough to overcome the threshold and initiate collapse. When we speak of the interstellar gas, we must also speak of dust. Cosmic dust is not like the dust in your house. It consists of very small particles, often only 1,000th of a millimeter in diameter, made of heavy elements such as carbon and silicates. These dust grains are produced in the atmospheres of old stars, especially red giant stars, and are blown into space by stellar winds. They are also produced in supernova explosions. Although dust accounts for only about 1% of the mass of the interstellar gas, it has a disproportionate effect relative to its mass. Dust is very effective at absorbing and scattering light, especially visible and ultraviolet light. That is why when we look along the plane of the Milky Way, we see a dark band running along it. That dark band is not because there are no stars there, but because light from stars behind is obscured by dust. This phenomenon is called extinction, and it is a major challenge for astronomers trying to observe distant stars in the galactic disk. Fortunately, dust does not block all wavelengths equally. It absorbs blue light more than red light, a phenomenon called reddening between stars. More importantly, dust is almost transparent to infrared light and radio waves, allowing astronomers to observe through the densest dust clouds. But dust is not just a nuisance for astronomers. It also plays a crucial role in star and planet formation. In cold, molecular clouds, dust acts as a surface where atoms can meet and combine to form molecules. Without dust, molecule formation would be much slower, and star formation would be more difficult. Moreover, dust is the raw material for forming rocky planets like Earth. When a new star is born, the dust around it collects into a disk called a protoplanetary disk. Within this disk, dust grains collide and stick together, gradually growing from tiny particles into rocks, planetesimals, and eventually planets. This process, called accretion, is how Earth and the other planets in the solar system formed about 4.5 billion years ago. So dust, though tiny and seemingly insignificant, is actually an essential component of the universe. It obscures light, but it also helps form molecules, stars, and planets. Each grain of dust is a small brick in the universe's enormous construction. In the story of the galaxy's life cycle, supernova play a central and decisive role. They are not merely explosions that mark the death of massive stars, but events that trigger the birth of new generations of stars. They are bridges between death and life, between an ending and a beginning. When a massive star, at least 8 times the mass of the Sun, exhausts the nuclear fuel in its core, nothing remains to resist gravity. The core collapses in a matter of seconds, compressing matter to unimaginable densities, and then the outer layers are blasted outward in a gigantic explosion. The energy released in a supernova is tremendous, equivalent to the energy the Sun emits over 10 billion years, yet released in only a few weeks. This explosion produces a shock wave, a front of matter and energy that expands into space at speeds of thousands of kilometers per second. When that shock wave encounters surrounding gas clouds, it compresses them, raising their density. And as we know, when the density increases enough, gravity can overcome gas pressure, and the cloud begins to collapse to form new stars. This process has been observed in many star-forming regions in our galaxy. Astronomers can see strings of young stars lining the expanding shells of old supernova remnants like pearls strung on a thread. These stars, called supernova-triggered stars, are born directly because of the explosion's impact. A famous example is the star-forming region in the Carina Nebula, where many supernova have exploded in the past, creating giant bubbles and triggering the formation of thousands of new stars. Scientists estimate that perhaps 10 to 20% of all the galaxy stars are formed through this mechanism, meaning supernova not only destroy, but also create, not only end, but also begin. But the role of supernovae does not stop there. They also heat the surrounding gas to temperatures of millions of degrees, creating hot bubbles that can extend for hundreds of light years. These supernova bubbles produce a multi-phase interstellar medium with hot and cold regions, dense and rarefied zones interwoven. This diversity is crucial for the galaxy's liveliness because it creates many different environments where different physical and chemical processes can occur. Furthermore, supernovae play a vital role in regulating the galaxy's star formation rate. By heating and stirring the gas, they make it harder for the gas to collapse and form stars, acting as a negative feedback mechanism. If too many stars form at once, there will be too many supernovae and star formation will slow. Conversely, if too few stars form, there will be fewer supernovae. The gas will cool and collapse more easily, and the star formation rate will rise. This self-regulation helps the galaxy maintain a relatively steady star formation rate over long periods. This may be one of the most beautiful and profound facts about our connection to the cosmos. Every atom in your body, except hydrogen, was forged inside a star or in a supernova explosion. You are not just made of stardust in a poetic sense, but in a literal sense. Think about this concretely. The carbon atoms in your DNA, the molecules that carry the genetic information that make you you, were created in the cores of massive red giant stars through a process called the triple alpha process. In this process, 3 helium nuclei collide and fuse to form a carbon nucleus. When those stars die, they eject their outer layers into space, and that carbon becomes part of the interstellar medium. The oxygen atoms in your water and in the air you breathe were created by nuclear fusion in even larger stars when helium and carbon combine. Nitrogen in your proteins formed in similar ways. Calcium in your bones and iron in your blood were produced in the deeper layers of massive stars as fusion created ever heavier elements. But the heaviest elements, like gold, silver, and uranium, are not formed in ordinary stars. They require far more extreme conditions found only in supernova explosions or in collisions between two neutron stars. In these violent events, temperatures and pressures reach extremes, and heavy nuclei can be synthesized through a process called rapid neutron capture. So, every atom in you has a cosmic history. It was born in the hot core of a star, was released in an explosion or a gentler stellar wind, drifted through interstellar space for millions or billions of years, and was finally incorporated into the molecular cloud from which the sun and the solar system formed. Then, through geological processes on Earth and the chain of biological food webs, it found its way into your body. Astronomer Carl Sagan once said, "We are made of star stuff. We are a way for the universe to know itself." That is not romantic poetry, but sober, scientific truth. Your existence is the result of billions of years of cosmic evolution, of countless stars living and dying, and of complex physical processes occurring under extreme conditions that we cannot reproduce on Earth. And when you are gone, when your body decays and returns to the soil, those atoms do not vanish. They continue to exist, becoming part of the air, the water, the plants, and the animals. And perhaps one day, after many billions of years, when the sun dies and the earth is no more, some of those atoms may find their way into a new star, a new planet, or perhaps a new living being. The cycle continues with no clear beginning and no final end, only continual transformation. Now let us speak about a lesser known but crucial process for the life of the galaxy, the galactic fountain. This is a circulation cycle of gas between the galactic disk, where stars are active, and the halo, the vast region surrounding the disk. The process works like this. In the galactic disk, especially in regions of intense star formation, there are many young, hot, massive stars. These stars produce strong stellar winds and eventually explode as supernovae. All this energy heats the surrounding gas to temperatures of millions of degrees and drives it up out of the disk at high speeds, sometimes reaching a few hundred kilometers per second. This hot gas rises high into the halo, perhaps up to a few thousand light years above the disk plane. There, it begins to cool, losing energy through radiation. As it cools, it also slows down, and eventually the galaxy's gravity pulls it back. The cooled gas falls back into the disk, where it can be incorporated into new molecular clouds and participate in the next cycle of star formation. The process is like a fountain, with gas pumped up from the disk and falling back, forming a circulation loop. But unlike an ordinary fountain, This process occurs on a gigantic scale, across thousands of light years of space and tens of millions of years of time. The galactic fountain has several important consequences. First, it helps mix gas in the galaxy, distributing heavy elements produced in stars and supernovae throughout the galaxy. Without this mixing, heavy elements would remain concentrated where they were produced, and other regions of the galaxy would stay metal poor. This mixing is why the chemical composition of gas across the galaxy is relatively uniform. Second, the fountain helps regulate the star formation rate. By driving gas out of the disk, it reduces the amount of fuel available for star formation, slowing the process. But when the gas falls back, it supplies fresh fuel for new star formation. This is a complex feedback mechanism that helps the galaxy maintain balance. Third, the fountain can affect the distribution of dark matter. As gas moves up and down through the halo, it interacts gravitationally with dark matter and may influence its distribution over time. This is an area of active research, and scientists are still trying to understand the full impact of the fountain on galactic structure. Observing galactic fountains is not easy because the hot gas radiates primarily in X-rays and ultraviolet, requiring space telescopes to detect. But in recent decades, observations from satellites such as Chandra and XMM Newton have provided increasingly clear evidence for fountains and helped us understand how they operate. All of these processes connect in a complex web of cause and effect, action and reaction. Nothing in the galaxy exists in isolation. Everything is connected. Everything influences everything else, and all participate in the grand dance of cosmic transformation. Among the hundreds of billions of stars in the Milky Way, how many planets are there? How many worlds like Earth? And are we alone in this vast galaxy? These are questions that have haunted humanity for millennia, and only in the last few decades have we begun to have observational answers rather than pure speculation. There was a time when we did not even know whether planets existed beyond our solar system. Stars are so distant, and planets so small and faint compared with their host stars, that detecting an exoplanet is like trying to see a firefly next to a spotlight from thousands of kilometers away. But in 1995, astronomers Michel Mayor and Didier Queloz announced the first detection of a planet orbiting a sun-like star, a star called 51 Pegasi. This planet, named 51 Pegasi b, is a giant gas world larger than Jupiter, but orbiting extremely close to its star, completing an orbit in only 4 days. This was an entirely unexpected configuration, unlike anything in our solar system, and it opened a new era in astronomy. Since then, more than 5,000 exoplanets have been confirmed, and the number continues to grow rapidly. These planets are found around different types of stars, at a variety of distances, with varying sizes and compositions. We have found rocky planets smaller than Earth, gas giants larger than Jupiter, blisteringly hot worlds orbiting very close to their stars, and icy planets far from their stars. The most common methods for detecting exoplanets are the transit method, when a planet crosses in front of its host star from our viewpoint and causes a slight dip in the star's brightness, and the radial velocity method, which measures the star's tiny wobble caused by the planet's gravitational pull. From the dimming, we can determine the planet's size, and from the wobble, we can estimate its mass. NASA's Kepler satellite, launched in 2009, revolutionized the field. Over its 9-year mission, Kepler observed more than 500,000 stars and discovered thousands of planets. Kepler's data allowed scientists to estimate that on average, each star in the Milky Way has at least one planet. That implies there are at least 200 billion planets in our galaxy and possibly many more. That number is astounding. 200 billion worlds, each with its own geology, climate, and history. Some may have mountains taller than Everest, oceans deeper than the Mariana Trench, storms much fiercer than anything on Earth. And some, just a small fraction, may have conditions suitable for life. This discovery has completely changed how we view our place in the universe. Earth is no longer a unique exception, but one of countless worlds. The solar system is not unique, but one of many planetary systems. And that naturally raises the question: if there are so many planets, how many of them might host life? But not all planets orbit a star. There exists a mysterious and intriguing population called rogue planets, worlds floating freely through interstellar space without a host star. These planets form like ordinary planets within the gas and dust disk around a young star, but for some reason are ejected from their planetary systems. This can happen through gravitational interactions with other planets, especially massive gas giants. During the early chaotic stages of a planetary system, when orbits are not yet stable, planets can scatter one another, and some may gain enough energy to escape completely. They can also be ejected by a close encounter with another star, if the planetary system lies in a dense star cluster. Or they might even form independently by direct collapse of a small gas cloud, like stars, but with much lower mass. Regardless of their origin, rogue planets are lonely worlds drifting in the cosmic darkness without the light of a star to warm them. They must be extremely cold, with surface temperatures of only a few tens of degrees above absolute zero. Without sunlight, there is no day and night, only eternal night. Detecting rogue planets is not easy because they emit very little light, but they can be detected through the effect of gravitational microlensing. When a rogue planet passes in front of a more distant star, its gravity bends the star's light, making the star temporarily appear brighter. This brightening lasts only a few hours to a few days, but it can be detected by sensitive telescopes. Microlensing surveys have found many events that may be caused by rogue planets. Based on these observations, scientists estimate that there may be billions or even trillions of rogue planets in the Milky Way, possibly outnumbering stars. This means that most planets in the galaxy may not orbit any star. The idea of worlds drifting in eternal darkness is both sad and fascinating. They are exiled worlds, refugees from planetary systems long gone. But are they completely dead? Some scientists have speculated that a large rogue planet with a thick layer of ice could maintain a subsurface ocean kept warm by heat from its core. And if liquid water exists, could life be possible? It is a speculative possibility, but it reminds us that life may find a foothold in the most unexpected places. When we think about the possibility of life, we often think about the concept of the habitable zone around a star, sometimes called the Goldilocks zone, where temperatures are just right for liquid water to exist on a planet's surface. Too close to the star, and water will evaporate. Too far, and it will freeze. At the right distance, conditions may be suitable for life as we know it. But there is a lesser-known concept called the galactic habitable zone. This is not a region around a single star, but a region in the entire galaxy where conditions are favorable for the development of life on planets. The idea is this. Too close to the galactic center, the stellar density is very high, with many supernovae, intense radiation, and a supermassive black hole that can produce high-energy phenomena. This environment may be too violent and unstable for life to persist over long periods. A nearby supernova could destroy a planet's ozone layer, exposing the surface to lethal ultraviolet radiation. Or, radiation from the black hole could harm any organisms on nearby planets. On the other hand, too far from the galactic center, the metal abundance in the gas decreases. Remember that in astronomy, metals mean any elements heavier than hydrogen and helium. These elements are critical for forming rocky planets and for the chemistry of life. Carbon, oxygen, nitrogen, and phosphorus are all metals by astronomical definition. Without enough of these elements, rocky planets may not form, or, if they do, they may lack the necessary ingredients for life. Therefore, the galactic habitable zone is a ring-shaped band around the galactic center, not too close and not too far, with moderate conditions. Estimates vary on the precise location of this zone, but most agree that it extends from about 13,000 to 33,000 light-years from the galactic center, with a width of about 20,000 light-years. The solar system, at a distance of about 27,000 light-years from the center, lies within this zone. This may not be a coincidence. Life may only be able to develop to high complexity in places like this, where the environment is stable and the necessary elements are abundant. If so, then when we search for intelligent life in the galaxy, we should focus on this region. However, the galactic habitable zone concept remains controversial. Some scientists argue that life may adapt to far more varied conditions than we expect, and might arise even in places we consider unfavorable. Indeed, life on Earth has demonstrated remarkable adaptability, surviving in extreme environments from deep ocean hydrothermal vents to arid deserts to Antarctic ice. But whether or not the galactic habitable zone is accurate, the idea reminds us that our position in the galaxy may not be accidental. We may find answers within our lifetime, or the question may persist for many generations. But simply asking the question and searching has already changed us. It has expanded our perspective and made us realize that the universe is larger, more diverse, and more wondrous than we could ever imagine. When you look up at the night sky and see the twinkling stars, you are seeing only a very small part of the story. What your eyes see is visible light, only a narrow band in the vast electromagnetic spectrum. The Milky Way emits energy at all wavelengths, from the longest radio waves to the shortest gamma rays, and each wavelength carries its own information. Starting with radio waves, the longest electromagnetic waves with wavelengths from a few millimeters to many kilometers. the galaxy emits radio waves from many different sources. Fast-moving electrons in magnetic fields emit synchrotron radiation, a characteristic type of radio emission. Cold hydrogen gas clouds emit the famous 21-centimeter line, a spectral line first detected in 1951 by Harold Ewan and Edward Purcell. This line has become one of the most important tools for mapping the distribution of hydrogen in the galaxy. Pulsars, rapidly rotating neutron stars with periods from a few milliseconds to a few seconds, emit beams of radio waves sweeping through space like lighthouse beams. Each time the beam passes Earth, we detect a brief pulse. And from the time between pulses, we can determine the pulsar's rotation rate with astonishing precision. Some pulsars, called millisecond pulsars, rotate hundreds of times per second and have periods so stable that they rival our best atomic clocks. Next is infrared radiation, emitted by warmer objects that are not hot enough to shine visibly. Cosmic dust, warmed by starlight to temperatures of only a few tens of degrees above absolute zero, emits primarily in the far infrared. Brown dwarfs, the failed stars too small to sustain nuclear fusion, have surface temperatures of only a few hundred to a few thousand degrees and emit most of their energy in the near infrared. Observing the galaxy in infrared reveals star-forming regions hidden behind dense dust clouds where visible light cannot pass. The Spitzer Space Telescope, which operated from 2003 to 2020, provided stunning infrared images of the Milky Way, revealing the structure of the spiral arms and the locations of star-forming regions more clearly than ever. The James Webb Space Telescope, launched in 2021, is continuing this legacy with much higher sensitivity and resolution. Visible light, the narrow band that our eyes evolved to see, comes from stars with surface temperatures of about 3,000 to 30,000 Kelvin. The Sun, with a surface temperature of about 5,700 degrees, emits most of its energy in the visible range, particularly in green-yellow wavelengths. This is why our eyes are most sensitive to this range of wavelengths, an evolutionary adaptation to make use of the most common light from our star. Ultraviolet light, with wavelengths shorter than violet, comes from hotter stars, particularly blue giants with surface temperatures up to 50,000 degrees or more. Ultraviolet light is also emitted from the hot accretion disks around compact objects such as white dwarfs, neutron stars, and black holes. However, most ultraviolet light from the galaxy is absorbed by Earth's atmosphere. So to observe at these wavelengths, we need to use space telescopes such as the Galaxy Evolution Explorer or Hubble. X-rays, with much higher energy, come from extremely energetic processes. Gas, heated to millions of degrees, emits X-rays through thermal radiation. This occurs in supernova remnants, where shock waves heat the gas to extreme temperatures. It also occurs in accretion disks around black holes and neutron stars, where matter falls in at nearly the speed of light, and friction converts kinetic energy into intense heat. Space-based X-ray observatories, such as Chandra and M. Newton, have revolutionized our understanding of high-energy processes in the galaxy. They have detected thousands of X-ray sources, from X-ray binary systems where a neutron star or black hole is drawing in matter from a companion star, to expanding supernova remnants, to the hot gas that fills the galactic halo. Finally, there are gamma rays, the highest energy form of electromagnetic radiation. Each gamma ray photon carries energy millions of times greater than a photon of visible light. 1 billion stars. This is a number difficult to grasp. It is about 1% of all the stars in the galaxy, yet it is enough to create a three-dimensional map of unparalleled detail of the galaxy's structure and motions. Imagine having to measure the exact positions of 1 billion objects moving through three-dimensional space, each at a different distance and moving in a different direction. That is the challenge Gaia is undertaking. Gaia operates by using a technique called parallax measurement. As Earth orbits the Sun, we observe stars from slightly different positions in space, and nearby stars appear to shift slightly relative to more distant background stars. By measuring this shift, called parallax, we can calculate the distance to the star. Gaia can measure parallax with an accuracy of a few tens of microarc seconds, equivalent to measuring the diameter of a human hair from a distance of 1,000 kilometers. But Gaia does not just measure positions. It also measures the proper motions of stars, meaning how they move across the sky over time due to their actual motion through space. By combining parallax with proper motion and with radial velocity measurements from spectroscopy, we can determine a star's full three-dimensional velocity through space. This is extremely valuable information for understanding the dynamics of the galaxy. Since beginning operations, Gaia has released multiple data sets, each containing more detailed and precise information. The third data release, published in 2022, contains information on more than 1.8 billion stars, including positions, parallaxes, proper motions, brightnesses, colors, and for many stars, radial velocities and chemical compositions. Data from Gaia has led to countless discoveries. It has helped astronomers identify stellar streams from dwarf galaxies that have been accreted, revealing the complex merger history of the Milky Way. It has provided evidence for density waves in the galactic disk, possibly caused by interactions with the Sagittarius dwarf galaxy. It has helped identify thousands of open clusters and globular clusters and has tracked their orbits. It has discovered thousands of variable stars, binary stars, and stars with planets. Most importantly, Gaia is giving us a three-dimensional view of the Milky Way, unlike anything we have ever had. For the first time, we can see the structure of the galaxy not only as a two-dimensional projection on the sky, but as a three-dimensional object in space, with stars at different distances and moving in different directions. This is a leap in understanding comparable to moving from a flat map to a three-dimensional globe of Earth. While Gaia observes in visible wavelengths, another family of instruments observes an entirely different part of the electromagnetic spectrum: radio telescopes. These instruments have opened a completely new window for observing the galaxy, allowing us to see what lies behind thick cosmic dust and revealing physical processes that visible light cannot detect. Radio waves have much longer wavelengths than visible light, ranging from a few millimeters to several meters or even longer. Because of their long wavelengths, radio waves are not strongly scattered by small dust grains the way visible light is. This means radio waves can pass through even the densest dust clouds in the galaxy, allowing us to see into star-forming regions deep within molecular clouds, places that optical telescopes cannot penetrate. One of the most important radio telescopes for studying the Milky Way is the Very Large Array, or VLA, in New Mexico, United States. The VLA consists of 27 radio antennas, each 25 meters in diameter, arranged in a Y shape spanning up to 36 kilometers. By combining the signals from all these antennas using a technique called interferometry, the VLA can achieve angular resolution equivalent to a single dish 36 kilometers wide, allowing it to produce incredibly detailed radio images of astronomical objects. The VLA and other radio telescopes have been used to map the distribution of hydrogen gas in the Milky Way by observing the 21-centimeter line. These maps have revealed the spiral structure of the galaxy in great detail, showing spiral arms far more clearly than what we can see in visible light because of dust obscuration. They have also allowed astronomers to measure the rotation speed of gas at different distances from the galactic center, providing some of the strongest evidence for the existence of dark matter. Radio telescopes have also detected and studied thousands of pulsars in the Milky Way. Pulsars emit powerful beams of radio waves from their magnetic poles, and as they rotate, these beams sweep across space. If a beam sweeps across Earth, we detect a radio pulse, and by measuring the precise timing of these pulses, we can learn a great deal about the pulsar and the environment around it. More recently, a new generation of radio telescopes has been built or is under construction, promising to revolutionize radio astronomy. The Atacama Large Millimeter Submillimeter Array, or ALMA, in Chile consists of 66 antennas observing at millimeter and submillimeter wavelengths, allowing it to study cold molecular clouds and the process of star formation with unprecedented detail. The Square Kilometer Array, or SKA, currently being built in Australia and South Africa, will be the world's largest radio telescope when completed, with a total collecting area of about 1 square kilometer, promising sensitivity and resolution never before achieved. But not all of our tools are complex machines on the ground or in space. Some of the most important tools for measuring distances in the universe are stars themselves, specifically variable stars. These stars change their brightness over time in predictable ways, and by studying this variation, we can determine their true luminosity and from that, their distance. The most important type of variable star for distance measurement is the Cepheid variable, named after the prototype star Delta Cephei. Cepheids are giant or supergiant stars undergoing a stage of their evolution in which they are unstable in pulsation. They expand and contract cyclically, and as they do, their brightness changes in a regular pattern. The crucial discovery, first made by astronomer Henrietta Swan Leavitt in 1912, is that there is a tight relationship between the pulsation period of a Cepheid and its average absolute luminosity. Cepheids with longer periods are brighter. This relationship, called the period luminosity relation, allows us to use Cepheids as standard candles for distance measurement. Here is how it works. First, We observe a Cepheid and measure its pulsation period, the time required for its brightness to go from maximum to minimum and back again. From this period, using the period luminosity relation, we can determine the star's absolute luminosity, meaning its true brightness if it were placed at a standard distance. We then compare this absolute luminosity to the apparent brightness we observe. The difference between the two tells us how far away the star is. Cepheids are bright enough to be seen in nearby galaxies, allowing us to measure the distances to those galaxies with good accuracy. Edwin Hubble used Cepheids in the 1920s to measure the distances to the Andromeda Galaxy and other galaxies, proving that they are separate island universes beyond the Milky Way, rather than nebulae within our galaxy as previously thought. This was one of the most important discoveries in astronomy, dramatically expanding the known scale of the universe. Beyond Cepheids, many other types of variable stars are also used as distance indicators. R are Lyrae stars, similar to Cepheids but fainter and with shorter periods, are used to measure distances to globular clusters and stars in the halo of the Milky Way. Type 1, A supernovae, extremely bright explosions that occur when a white dwarf accretes enough material from a companion star to exceed its mass limit, have very uniform peak luminosities, and can be seen in galaxies billions of light years away, making them essential tools for cosmology. All of these distance indicators together form a cosmic distance ladder, with each rung calibrated by the one below it and extending our reach farther into the universe. From parallax for nearby stars to variable stars for nearby galaxies to supernovae for distant galaxies, we have built a measurement system that allows us to map the universe at every scale. But these tools are not just machines and methods. They are manifestations of human curiosity, of our desire to understand, of our drive to explore. Every observation, every measurement, every discovery is the result of centuries of accumulated effort by countless scientists and engineers who devoted their lives to building these tools and using them to expand our knowledge. And these tools continue to improve. Each generation of telescopes is more powerful than the last, each new technique more sophisticated than the one before. The James Webb Space Telescope, launched in 2021, is observing the universe in infrared with unprecedented sensitivity, revealing distant galaxies and forming planetary systems in stunning detail. Gravitational wave observatories, such as LIGO, are detecting ripples in space-time from collisions of black holes and neutron stars, opening an entirely new window onto the universe. Next-generation telescopes are being designed and built, promising discoveries we can only dream of today. On this long journey, we began with simple questions. What is the Milky Way? How is it structured? How did it form and evolve? And we have found rich and complex answers. Answers that reveal a galaxy more dynamic, diverse, and wondrous than anything we could have imagined. We have seen that the Milky Way is a 13-billion-year-old spiral galaxy containing hundreds of billions of stars and trillions of planets, wrapped in a massive halo of dark matter. We have seen that it was shaped by past collisions and will collide with Andromeda in the future. We have seen that it is filled with gas, dust, radiation across all wavelengths, cosmic rays, and neutrinos. We have seen that it is part of the local group, the Laniakea supercluster, and the vast cosmic structure. And most importantly, we have seen that we, small beings on a small planet orbiting an ordinary star in a quiet minor arm of the galaxy, are an inseparable part of all this. Every atom in our bodies was forged in the cores of dying stars. We are made of stardust, and we are the way the universe knows itself. Take one final deep breath in this journey. Feel the wonder and beauty of everything we have learned. Feel the connection between you and the galaxy, between you and the universe. And know that this journey of discovery has never ended. There will always be more mysteries to solve, more discoveries to make, more wonders to behold. But now, allow yourself to rest. Let all these images and ideas settle in your mind like stardust settling from a supernova explosion, slowly, gently, finding a resting place. Let your breath become slower and deeper, and let sleep come naturally, like night following a long day. Sleep well, my dear friend. And when you dream, perhaps you will dream of the stars.